Good morning. In this video, we'll introduce the RVfpga platform, also known as RVfpga. RVfpga is a course covering various aspects of computer architecture, specifically how to run a commercial RISC-V core like VIR and a system on chip on an FPGA and in simulators. Note that VR has been the name for some time now. Originally, the core family was called Swerve. It also shows how to program the SoC, both in RISC-V assembly and C language. It explores adding functionality to the SoC, like modifying and adding I/O peripherals, and at the RISC-V core level, it explains how the VIR core works and how we can modify it to add new instructions and analyze the memory hierarchy. The teaching package was developed by Imagination Technologies, primarily with academic and industry partners. Upon completing the RVfpga course, students will have a commercial RISC-V processor and SoC ready for use on boards and simulators, understanding the SoC, core and entire RISC-V ecosystem details which they can both use and modify. RVfpga comprises two courses. The first, simply called RVfpga, covers the VR core, memory system, and some peripherals. The second, RVfpga SoC, shows how to build a RISC-V SoC in Vivado, install the Zephyr real-time OS and use it to run programs, and finally how to use TensorFlow machine learning platform to run basic programs. Both courses are available for free on the Imagination Technologies University program page. To tackle the RVfpga course effectively, it's recommended to have knowledge in certain computer architecture areas, specifically digital design, high-level languages like C, assembly language, preferably RISC-V, as well as RISC-V instruction, set architecture or microarchitecture and memory systems. All this is covered extensively in Digital Design and Computer Architecture, RISC-V edition by Sarah and David Harris, published by Elsevier in 2021, and these aspects are also thoroughly explored through practical exercises in the RVfpga course. This is the recommended book, Digital Design and Computer Architecture, RISC-V edition by Sarah and David Harris. Note that Sarah Harris is also a co-author of this RVfpga material, and the book can be found in many bookstores and likely in most university libraries worldwide. Well, regarding RVfpga software and hardware, we should first note that hardware is optional as all exercises can be run in a simulator. However, you can purchase this hardware. There are various FPGA boards with different costs and features. The most comprehensive and priciest is Digilent's Nexus A7 or its predecessor, the Nexus 4 DDR. Then more budget-friendly options include the Digilant Basis 3 or Real Digital's board called Bullion, which is quite affordable and well equipped. As mentioned, hardware is optional and all software is free and open source. If we want to synthesize for FPGA execution, we need Vivado, the free Webpack version, like 2022.2 or other compatible versions. Works fine. SDK supports both Visual Studio Code and the platform.io extensions such as Catapult, Imagination's proprietary SDK, and then some additional tools are also necessary like Verilator to run the simulators, GTK Wave and other apps not mentioned here. As for operating systems, all three are supported, Linux, Mac and Windows, though we'll develop this course on a virtual machine, specifically an Ubuntu 22.04 virtual machine that can run on any operating system. Regarding the core and SoC, the core is VR, both LH1 and LL2, and the SoC is Chips Alliances based on these VIR cores called VirWolf. Looking at the typical SoC hierarchy with a CPU and surrounding elements that can run on a board, we can see the different levels of the RVfpga hierarchy. At the lowest level, the core, we have the VEX RISC of EH1 and EL2, an open source core initially developed by Western Digital, now hosted on the Chips Alliance website. Here are the links for EH1 and EL2. The core integrates into a larger structure called the core complex, including data and instruction scratchpads, instruction cache, interrupt controller, bus interfaces, and debug unit. Above that we have the SoC, which is VEX RISC in an extended version. VEX RISC is a free open source SoC available at this link. We've added some elements to it, originally including a boot ROM, UART interface, system controller, AXI and Wishbone interconnects, a bridge between them, and an SPI controller. We've added 4 more peripherals, a GPIO, a PTC module, an extra SPI, and a 7-segment display controller. Moving up the hierarchy, we find the implementation on the board or in the simulator. For boards, we support 3 different options with varying prices and features. To integrate the core into the board, we need to add elements like a DDR2 memory interface, a clock domain crossing, a JTAG interface unit, and a clock generator. Then we have the simulator version, which is based on Verilator. We also offer Whisper and Instruction Set Simulator available with the RWfpga package. Let's analyze the RVfpga system based on Vir A1 in more detail. First, we show the complete system in this figure. As we saw in the previous table, it consists of the core Vir H1, the core complex, which adds some elements listed here to the core. Then here it's called Swirwolf or VirWolf SoC, the extended version, as it incorporates both the elements that VirWolf already has and those we've added, which can only be implemented on the board in this case only on the N-axis, because the EH1 core is too large to fit in the basis 3 or Boolean, so it can only be used on the N-axis and also in the simulator with the different options we saw. We'll examine each hierarchy element in more detail, starting with core, ver H1 and core complex. Here we see the core complex figure showing the core in blue and additional elements added by core complex in green. It's a free and open use core initially developed by Western Digital. It's 32-bit, includes the base instruction set and C&M extensions. It's two-way superscalar with a 9-stage pipeline. It allows for separate instruction and data scratch pads, has an instruction cache but no data cache, an interrupt controller, and a debug unit compatible with the RVfpga debug specification. It also has a series of buses configurable as AXI4 or HB Elite. In our case, we'll use the AXI bus. The core EH1 is integrated into the VRWolf extended SoC shown in this figure. As we can see, the core complex connects via an AXI bus to a bridge that converts AXI bus signals to Wishbone and vice versa, and then the Wishbone bus connects to the controllers of the devices available in the SoC. This table shows the address range for each of the elements in the previous figure. We can use various tools to run the core and SoC. On the right side of the figure we see the back end, which is the VRWolf extended SoC, and on the left we see the front end. The top arrow shows onboard execution on the Nexys A7 board, for which we must create the SoC bit stream, while the bottom arrow shows simulator versions. We have 3 Verilator-based simulators. The first, RVfpga BitBow, simulates a virtual board. The second, RVfpga Trace, captures an application's execution trace on the SoC. And the last, RVfpga Pipeline, allows us to visualize instruction execution through the EH1 pipeline. Next, we'll provide a more detailed explanation of each of these elements. The first option is onboard execution using the Digilent Nexys A7 board. We surround the SoC with additional elements to run on the board and communicate with peripherals. Specifically, we add a clock generator that produces a 50 MHz clock, which the core and other elements will use. We also add a DRAM controller not included in the SoC, but it can communicate via AXI bus and has reserved memory for it. This controller connects to the board's DDR2 memory plus a clock domain and JTAG logic. For peripherals besides DDR2, UART can connect to a console, board, LEDs and switches, accelerometer, flash, SPI flash memory and 7-segment displays can be used. The Nexys A7 board has an Arctic 7 FPGA and many peripherals. In addition to the ones we've mentioned, it includes a temperature sensor, a microphone, and a few others. These extra peripherals can be connected to the chip using the right controllers. The board can be bought through various channels, some of which we show here. For simulation, the RWFpga trace simulator lets us generate a trace of the chip's internal signals as it runs a program. We can then view this trace with GTK Wave and analyze the various internal signals. For instance, in this figure we can see how two instructions, a multiplication and an addition, pass through different pipeline stages. In the trace, we see the main signals from each of the stages, from decoding to write-back. Another simulation option we have is RWFpga BitBo. In this case, a virtual board simulates the RWFpga system and communicates with some simulated peripherals. Will simulate the same components as in the physical board version. The program shown in the figure reads switch states and displays them via LEDs. So switches in the up position light up their corresponding LEDs, while those in the down position keep the LEDs off. Note that any program working in the simulator will function identically on the actual board, highlighting the simulator's utility. Lastly, we can also simulate or visualize program execution through the EH1 pipeline. The RWFpga pipeline simulator, as seen in the figure, shows stages from decode to write-back, excluding the first three. We can view instructions at each stage in the different paths, noting some empty paths, which would contain bubbles due to dependencies or other reasons, and we can also see the core's main signals. For instance, in the integer pipes, we can observe input operands, ALU results in the OUT signal, and how results propagate until they're finally written to the register bank in the write-back stage. Regarding the RDPGA system based on Core VRL2, the structure is similar with a few key differences we'll highlight. First, we see three different figures because we can now run the system on three distinct boards, the Nexus A7 as before, plus the Basis 3 and the Boolean. This is because the Core L2 is much smaller than the EH1 and fits on compact boards like Basis 3 or Boolean. Also, the core is now L2, not EH1, and there's a different core complex. The other differences mainly concern peripherals. These boards lack some Nexus A7 peripherals, so certain features aren't available on all versions. Like with EH1, we'll examine the EL2 system's hierarchy levels, starting with the core and core complex EL2. Here's the figure illustrated. As we can see, everything's the same except the core, which is smaller in this case, as it's a core with a 4-stage pipeline and single issue instead of being superscalar. For the shock, we again have the Beard-Wolf extended shock based on EL2 instead of EH1, which includes the same elements, with the exception, as mentioned earlier, that some peripherals aren't available on certain boards, so they won't be used or included. Lastly, we have the same simulation tools, 3 varilator-based simulators, BitBo, Pipeline and Trace. Note that BitBow works on all three boards. We also have the instruction set simulator, Whisper and hardware support for three boards. Nexus A7, Basis 3 and Boolean. The Nexus version is identical to what we saw before with the same peripherals. The only difference is that the shock is based on EL2 instead of EH1. This core runs at a lower frequency, so the clock is 12.5 MHz instead of the 50 MHz used for EH1. The Basis version is similar, but with fewer peripherals. It supports UART, SPI for flash memory, 16 LEDs and switches, and 4-digit 7-segment displays. The next slide shows the Basis 3 board with a smaller Arctic 7 than Nexus A7, fewer peripherals, and available in different channels. Finally, the Boolean version has even fewer peripherals, 1 UART, 16 LEDs, 16 switches, and 8-digit 7-segment displays. This slide shows the Boolean board with a Spartan 7 FPGA, sized between Basis 3 and Nexus A7, but still too small for EH. The Boolean board has a different FPGA, a Spartan 7. It's mid-sized between Basis 3 and Nexus A7, but can't fit EH1. It includes various peripherals and is available for purchase on Real Digital's website and on some other websites as well. The RWfpga package includes various documents, with the Getting Started guide being the first one we should use. This document introduces the course starting with a RVfpga architecture review and a thorough analysis of the RWfpga system, similar to what we just did, including detailed descriptions of the cores, the shock, and how to use them with different tools. It also provides instructions for running RWfpga on the 3 operating systems where you can install the various tools. The only one not supporting all 3 is Vivado, as it's unavailable for macOS. Mac users will need to run Vivado on one of the other 2 operating systems, likely through a virtual machine. Then platform.io, Catapult, simulation tools, board drivers, all that is available on any of the 3 operating systems. The Getting Started guide also provides detailed instructions on writing, simulating, and running programs in Shock through examples. It includes 3 examples in RISC V assembly and 4 in high-level C language. One example, the LED switches, is provided in both languages. These examples either run algorithms or interact with peripherals to showcase various functionalities. For instance, one calculates vector dot products, while another blinks an LED on the board. The guide explains how to run these on supported boards, Nexus, A7, Basis 3, Boolean, and simulation tools, Whisper, BitBow, Pipeline, Trace. Finally, the guide includes appendices explaining various topics, like using toolchain and OpenOCD via command line instead of Catapult SDK or Platform I/O. The course also features practical exercises on different aspects of computer architecture. First, it includes 4 programming exercises covering both assembly and C languages. The first exercise explores C programming on the board and various simulators and introduces Western Digital's BSP and PSP for tasks like terminal printing and interrupt management. The second exercise introduces RISC-TV assembly language, with examples and exercises using all available tools. Practice 3 covers function calls and the RISC-CV calling convention standard. The fourth exercise involves an image processing application that combines C and assembly code. Next, we have a series of input-output exercises. In the first one, Practice 5, we'll show how to create a Vivado project in detail. This is needed to regenerate the bit stream after making changes to the SoC. Practice 6 introduces I/O using one of the simplest peripherals, the GPIO. We'll also do our first exercise extending the original SoC to support the board's buttons. This involves changing the SoC's Verilog code, making a new bit stream, and coding for the new peripheral. We'll do similar exercises in all the input-output practices in this section. Practice 7 covers managing 7-segment displays and extends this device from a more limited version that only shows a few digits to a more versatile one. Controller capable of displaying any combination of lit and unlit segments on the board. A counter exercise is conducted explaining the operation of a counter with various practice problems, and the project is expanded to use PWM for controlling another device on the board, the tricolor LEDs. Practice 9 introduces interrupt-based I/O management, highlighting its advantages over polling-based methods, and includes several hands-on exercises. Lastly, this section covers serial buses, featuring an exercise using the SPI bus-connected accelerometer. The final set of practices, 11 to 20, focus on VR cores, analyzing their function, instruction execution, and potential extensions in detail. Additionally, the memory hierarchy of the RWfpga system is examined. Practice 11 introduces EH1, explaining its core structure and how to use performance counters. Practices 12, 13, and 16 cover various instructions and their pipeline execution, arithmetic, memory, and conditional, unconditional jumps. Practices 14 to 16 demonstrate how the core manages structural data and control hazards. Practice 16 also explains the core's 2 branch predictors, a basic one and an advanced G-share. Practice 17 explores the superscalar execution available in EH1. Practice 18 analyzes how to add new instructions and hardware counters. Lastly, 19 and 20 examine the memory hierarchy, focusing on instruction cache and data instruction scratchpads. Additionally, commercial benchmarks are used to compare performance. The second package is RVfpga Shock. This package includes 5 practical exercises. The first uses Vivado's block design tool to create a simplified system on chip similar to RVfpga but with fewer peripherals. Practice 2 demonstrates using the shock created in Practice 1. Practice 3 shows how to create a shock with fuse shock, comparing it to Practice 1's approach. Practice 4 runs the Cepher real-time OS on the shock, and Practice 5 tests a TensorFlow Lite app with basic exercises.